In the early years of the Cold War, as military planners in both superpower blocs drafted contingency plans for large-scale conflict across Europe, Asia, and beyond, it became increasingly clear that the decisive factor in any sustained campaign would not be the first salvo of missiles or the initial armored thrust, but the invisible architecture that sustained forces once movement began, and thus military logistics networks, rail corridors, fuel depots, ammunition stockpiles, sea-lift fleets, airlift routes, maintenance hubs, and pre-positioned supply caches quietly became the structural foundation upon which war planning rested. While public discourse focused on nuclear arsenals and frontline divisions, internal planning documents emphasized tonnage calculations, transportation timelines, bridging capacity, fuel throughput, and repair cycle duration, recognizing that no operational concept could be credible without a logistics framework capable of sustaining it. Rail networks, in particular, were studied as arteries of mobilization, with planners mapping track gauges, load capacities, choke points, switching yards, and border crossings to determine how rapidly divisions could be repositioned or reinforced. Port facilities were evaluated for berthing space, crane capacity, storage depth, and vulnerability to disruption, as sealift remained essential for transoceanic reinforcement, especially for alliances dependent on rapid movement of heavy equipment. Airlift capabilities were expanded and standardized to support both strategic redeployment and emergency resupply. Yet airlift was recognized as capacity limited compared to maritime and rail throughput, making it a complement rather than substitute for bulk logistics. Fuel infrastructure, pipelines, storage tanks, refineries, and distribution nodes was incorporated into defense planning, as armored and mechanized forces consumed vast quantities of fuel whose uninterrupted supply was essential to operational tempo. Ammunition production and storage networks were structured to ensure dispersion and redundancy, preventing single-point failure from crippling sustained engagement. Maintenance and repair facilities were embedded within planning cycles, acknowledging that equipment attrition and wear would degrade combat power unless supported by organized recovery and refurbishment systems. Alliances coordinated logistics standards to ensure interoperability, standardizing ammunition calibers, fuel specifications, and spare parts protocols so that multinational forces could operate cohesively without bottleneck. Intelligence agencies monitored adversary logistics networks carefully, mapping rail density, depot locations, industrial output, and mobilization exercises to estimate how long sustained operations could be maintained and where vulnerabilities might exist. Traffic analysis extended beyond communications into freight movement, as shifts in rail activity or port congestion sometimes signaled mobilization or exercise activity. Pre-positioned equipment programs emerged as strategic solutions to deployment delay, storing heavy equipment forward while personnel would deploy by air, reflecting recognition that logistics timing shaped deterrence credibility. Stockpile management became a core planning discipline, with rotation schedules and replenishment cycles integrated into readiness assessments to ensure that munitions and fuel remained viable over extended periods. Infrastructure hardening and camouflage were applied to logistics nodes, acknowledging that adversaries would target supply networks to degrade combat effectiveness without necessarily engaging frontline forces directly. Redundancy was embedded deliberately, with alternate routes and dispersed depots constructed to mitigate disruption risk. Contingency plans incorporated repair of damaged rail lines and port facilities, integrating engineering units into logistics doctrine. Strategic mobility exercises tested throughput assumptions and exposed bottlenecks, leading to incremental improvements in network resilience. War games frequently demonstrated that even well-armed forces could stall if logistics pipelines faltered, reinforcing the understanding that supply networks determined operational endurance. By the 1960s, military logistics networks had become central variables in war planning models, shaping deployment strategies, force structure decisions, and alliance coordination frameworks. The Cold War confrontation thus elevated logistics from background function to strategic determinant, embedding rail yards, ports, pipelines, and warehouses into the calculus of deterrence. While rarely visible in public rhetoric, these networks quietly defined what was feasible in war planning, establishing the boundaries of operational ambition and shaping the credibility of every contingency drawn on strategic maps. As the Cold War matured into structured bloc confrontation, military planners increasingly understood that logistics networks were not merely supportive mechanisms, but decisive constraints that defined the pace, reach, and sustainability of any large-scale operation. And this realization reshaped war planning across continents. Force posture decisions were calibrated not only by the number of divisions available, but by the rail capacity required to move them, the port throughput needed to receive reinforcements, and the stockpile depth necessary to sustain combat beyond initial engagement. In Europe, rail density and track configuration became central variables in operational modeling, with planners calculating how quickly armored formations could shift between sectors, how rapidly reinforcements could cross borders, and where rail choke points might delay mobilization under pressure. Bridge load limits, tunnel clearances, and switching yard capacity were incorporated into war games, demonstrating that infrastructure geometry directly influenced strategic timing. Maritime logistics networks carried equal weight, as sealift fleets determined how rapidly heavy equipment could be transported across oceans, especially for alliances dependent on transatlantic reinforcement, and port infrastructure planning expanded to include surge capacity, offloading speed, and inland transport integration. Pre-positioned materiel programs were designed to reduce transit time by storing equipment forward while deploying personnel by air, reflecting a logistical compromise between speed and mass. Airlift expanded in capability but remained constrained by payload and range limitations, reinforcing the principle that strategic mobility depended on coordinated use of rail, sea, and air rather than reliance on a single mode. Fuel supply networks grew into extensive pipeline systems linking refineries, storage depots, and forward bases, acknowledging that mechanized warfare consumed extraordinary quantities of fuel whose interruption could halt offensive momentum. Planners measured fuel throughput in daily tonnage projections, aligning supply schedules with anticipated operational tempo. Ammunition logistics followed similar principles, with dispersed depots and rotation protocols designed to ensure continuous availability while minimizing vulnerability to concentrated attack. Maintenance networks were institutionalized, embedding repair battalions and recovery units within operational formations to prevent attrition from degrading force strength over time. Industrial production capacity was mapped carefully, linking civilian manufacturing plants to wartime conversion plans capable of sustaining extended conflict, and these conversion schedules were integrated into logistics modeling. Alliances standardized calibers, spare parts, and maintenance procedures to reduce friction in multinational operations, recognizing that interoperability at the supply level was as vital as coordination at the command level. Intelligence agencies monitored adversary logistics exercises, rail movements, industrial output statistics, and fuel storage construction to infer readiness levels and potential mobilization windows. Satellite imagery and reconnaissance flights increasingly focused on depot expansion, port upgrades, and pipeline construction as indicators of evolving strategic posture. Contingency plans included rapid infrastructure repair units capable of restoring damaged rail lines and bridges under combat conditions, acknowledging that logistics resilience required active restoration capacity. Dispersal strategies were refined to reduce vulnerability, with depots separated geographically and transport routes diversified to prevent single-point disruption. War games repeatedly demonstrated that ambitious operational concepts collapsed when supply projections proved unrealistic, reinforcing institutional discipline in aligning strategy with logistical feasibility. By the 1970s, logistics modeling had become highly quantitative, incorporating computer-assisted calculations of consumption rates, transit times, and stockpile depletion curves, embedding supply constraints directly into operational doctrine. The Cold War confrontation therefore produced a structural shift in how military power was conceptualized, placing logistics networks at the center of credible war planning and shaping strategic decisions long before any forces would move. The quiet expansion and reinforcement of these networks across rail corridors, maritime routes, airfields, pipelines, and warehouses defined the boundaries of operational possibility, ensuring that behind every projected advance stood a carefully engineered system of movement and supply without which the plan itself would have remained theoretical. As the 1970s unfolded, military logistics networks became even more deeply embedded within Cold War war planning as technological modernization, alliance expansion, and evolving doctrine placed greater emphasis on rapid reinforcement and sustained operational tempo. Planners increasingly modeled not only initial deployment speed, but endurance under protracted conditions, calculating how long mechanized formations could operate before fuel, ammunition, and spare parts depletion would require pause or withdrawal. Rail mobilization schedules were refined into detailed timetables, integrating civilian freight capacity with military surge requirements, and agreements were formalized to guarantee priority access to locomotives, rolling stock, and switching corridors during crisis. Port infrastructure upgrades were undertaken with dual-use justification, expanding container handling and storage capacity, while simultaneously enhancing the ability to offload heavy armor and bulk munitions at accelerated rates. Sealift planning incorporated pre-allocated vessel assignments, convoy routing schemes, and turnaround cycle optimization to ensure that transoceanic reinforcement would not stall at maritime bottlenecks. Airlift fleets expanded in payload capacity and range, yet planners remained acutely aware of lift-to-weight ratios, runway requirements, and maintenance cycles that constrained sustained air mobility, reinforcing that airlift complemented rather than replaced maritime bulk movement. Fuel distribution networks were extended and hardened, including buried pipelines, redundant pumping stations, and dispersed storage tanks designed to mitigate vulnerability while maintaining throughput. Consumption modeling grew more precise, accounting for vehicle type, terrain conditions, and expected operational intensity to estimate daily fuel requirements under various scenarios. Ammunition logistics were integrated into rolling resupply systems capable of replenishing frontline units without halting maneuver, and depot dispersal strategies reduced exposure to concentrated attack. Maintenance doctrine evolved to incorporate modular repair units capable of field-level restoration, minimizing the need for long-distance evacuation of damaged equipment and preserving operational continuity. Alliances invested heavily in standardization of spare parts, calibers, and fuel specifications, enabling multinational formations to share supply chains without friction and interoperability agreements extended to logistics software systems used for inventory tracking and movement scheduling. Intelligence agencies analyzed adversary infrastructure expansion, noting increases in rail spur construction, depot hardening, pipeline extension, and industrial output shifts as indicators of potential mobilization readiness. Satellite reconnaissance and aerial surveillance frequently prioritized observation of storage complexes and transport corridors to assess stockpile accumulation and surge capacity. Strategic mobility exercises were conducted regularly to test throughput assumptions, revealing bottlenecks in rail yard capacity, port crane availability, and convoy routing, leading to incremental infrastructure improvements. Contingency planning incorporated rapid bridge construction and rail repair units, recognizing that adversaries would likely target logistics arteries early in conflict to degrade reinforcement timelines. The concept of forward prepositioning expanded, placing heavy equipment, munitions, and fuel stocks near potential theaters to reduce reliance on long transit routes, thereby compressing deployment windows and enhancing deterrence credibility. Computer-assisted logistics modeling became more widespread, enabling planners to simulate consumption curves, resupply intervals, and attrition impacts under varied combat scenarios. Economic infrastructure planning increasingly overlapped with defense needs, as highway expansion, rail modernization, and port development were evaluated partly through strategic mobility criteria. By the mid-1970s, it was widely accepted within military establishments that logistics networks determined not only whether war could be fought, but how quickly and how long it could be sustained. The Cold War environment had elevated logistics from technical support to structural determinant, embedding movement corridors, fuel pipelines, storage depots, and maintenance hubs into the very logic of operational doctrine. Behind every contingency map and projected offensive lay a meticulously calculated network of supply and transport without which even the most ambitious strategic concept would have faltered, confirming that logistics infrastructure quietly shaped the boundaries of military ambition throughout the confrontation. By the late 1970s and into the early 1980s, military logistics networks were no longer treated as background support systems, but as dynamic strategic instruments that could influence deterrence credibility, escalation control, and alliance cohesion before any combat began. Planners increasingly recognized that visible logistics activity, stockpile expansion, rail, mobilization drills, sea lift preparation, fuel storage construction, could signal intent as clearly as troop movement, and therefore logistics became embedded not only in operational design, but in strategic messaging. Reinforcement doctrines were recalibrated to shorten deployment timelines, leading to expansion of pre-positioned equipment sites, hardened depots, and integrated transportation corridors capable of absorbing surge traffic without paralysis. Rail infrastructure modernization programs emphasized heavier axle loads, faster switching automation, and expanded yard capacity to handle the concentrated movement of armored units, while contingency plans mapped alternative routes to bypass potential choke points. Port facilities were upgraded to accelerate roll-on/roll-off discharge, container throughput, and inland transfer coordination, ensuring that sea-lift cargo could transition rapidly to rail and road networks without congestion. Airlift doctrine expanded strategic mobility, but remained governed by tonnage realities, reinforcing that rapid reinforcement depended on synchronized use of air corridors for personnel and maritime corridors for heavy materiel. Pipeline networks were extended and interconnected, creating layered fuel distribution systems capable of rerouting supply if segments were disrupted, and storage facilities were dispersed to prevent catastrophic loss. Ammunition stockpile management became more data-driven, integrating consumption modeling with production schedules to maintain depth without excess stagnation. Maintenance logistics were refined through modular repair packages and forward service hubs designed to sustain high-tempo operations while reducing equipment attrition. Alliances conducted regular mobility exercises to test interoperability of logistics software, rail gauge compatibility, port clearance procedures, and customs protocols, recognizing that bureaucratic delay could undermine strategic timelines as effectively as physical bottlenecks. Intelligence agencies tracked adversary logistics rehearsals closely, interpreting changes in depot construction, rail scheduling patterns, and fuel storage expansion as potential indicators of readiness shifts. Satellite imagery and signals intelligence provided continuous monitoring of freight density and transportation rhythms, enabling analysts to distinguish routine economic movement from military surge. Contingency doctrine assumed that logistics networks would be prime targets, prompting development of rapid engineering units capable of restoring damaged bridges, clearing rail debris, and repairing pipeline breaches under operational conditions. Computer-based logistics simulation matured significantly, allowing planners to test sustainment viability under multiple attrition scenarios and to identify thresholds beyond which offensive momentum would degrade. Economic infrastructure investment increasingly overlapped with defense requirements, as highway expansion, heavy load bridge construction, and port dredging were justified through both civilian and military rationale. By the early 1980s, logistics capacity had become a measurable component of strategic balance, influencing how quickly forces could mobilize, how deeply they could advance, and how long they could endure. The Cold War confrontation therefore institutionalized logistics networks as silent determinants of feasibility, shaping war planning parameters long before operational orders were drafted. Behind each force posture adjustment lay calculations of rail throughput, fuel flow rates, and sea lift cycle duration, confirming that the infrastructure of supply and movement quietly defined the limits of military ambition across both blocks. As the early to mid-1980s progressed, military logistics networks became increasingly intertwined with strategic mobility doctrine, technological modernization, and alliance reassurance policies, reinforcing their role as foundational elements of credible war planning. Planners focused not only on sustaining combat operations, but on compressing deployment timelines to signal readiness without triggering destabilizing escalation, leading to refined pre-positioning strategies in which heavy equipment, ammunition, and fuel were stored closer to potential theaters, while personnel remained stationed farther from the front. This approach reduced transit dependency on vulnerable sea and rail corridors during the critical early phase of a contingency, but required meticulous inventory management and continuous maintenance cycles to ensure stored materiel remained operational. Rail networks were digitized incrementally, incorporating computerized scheduling and yard management systems that improved throughput efficiency, while simultaneously centralizing control within nodes whose disruption could reverberate widely, prompting parallel investment in redundancy and manual override procedures. Port infrastructure planning emphasized rapid offload capability and inland integration, linking docks directly to rail spurs and highway corridors designed for heavy military transport, thereby minimizing transfer delays. Sea lift capacity assessments became routine components of strategic evaluation, with tonnage projections matched against reinforcement commitments to determine whether declared force postures could be supported realistically. Airlift modernization increased lift capacity, yet logistical doctrine maintained a clear distinction between rapid insertion and sustained supply, preserving reliance on maritime bulk movement for long-term operations. Fuel logistics expanded through interconnected pipeline systems and dispersed storage fields, reducing exposure to concentrated attack while maintaining flow continuity. Maintenance doctrine evolved toward modularity and forward repair, ensuring that equipment attrition did not cascade into operational paralysis during sustained engagement. Intelligence. Services monitored adversary industrial output, freight movement density, and depot construction as proxies for mobilization potential, recognizing that logistics activity often preceded visible troop movement. Satellite reconnaissance prioritized observation of rail yard congestion, port loading patterns, and pipeline expansion, enabling analysts to detect shifts in readiness posture. Mobility exercises were conducted with increasing realism, integrating civilian transportation authorities and commercial carriers into defense rehearsal frameworks, revealing administrative bottlenecks that were subsequently addressed through policy reform. Alliances refined standardization agreements to ensure compatibility of fuel types, munitions, calibers, and spare parts, reducing friction in multinational sustainment chains. Computer-assisted logistics modeling matured further, allowing planners to simulate extended attrition scenarios and evaluate sustainment thresholds under varied intensity conditions. Contingency plans incorporated rapid engineering units specialized in restoring damaged transport corridors, reinforcing the assumption that adversaries would attempt to degrade supply lines early in conflict. Economic infrastructure development was evaluated partly through strategic criteria, with heavy load bridge reinforcement, rail electrification, and port dredging serving both civilian commerce and military mobility objectives. By the mid-1980s, logistics networks were fully institutionalized as determinants of strategic credibility, shaping not only operational planning, but also alliance confidence and deterrence signaling. The Cold War had demonstrated repeatedly through war games and exercises that ambitious maneuver concepts collapsed when sustainment projections proved unrealistic, reinforcing disciplined alignment between strategic aspiration and logistical capacity. Behind every public posture statement and contingency scenario lay detailed calculations of fuel flow, ammunition turnover, maintenance cycles, and transport throughput, confirming that the quiet architecture of supply defined the operational boundaries of the era's military competition. As the late 1980s approached, military logistics networks remained central to war planning, even as broader geopolitical tensions began to shift, because the structural realities of movement, sustainment, and industrial capacity continued to define what any force could realistically accomplish in a large-scale contingency. Planners increasingly integrated logistics modeling with command and control systems, linking inventory databases, transportation scheduling platforms, and readiness assessments into unified frameworks capable of providing near real-time visibility into supply status and deployment timelines. This integration improved efficiency, but also highlighted dependencies, as centralized data systems became critical nodes whose disruption could impair decision-making, prompting parallel investment in backup procedures and distributed record-keeping. Rail and highway modernization projects were evaluated explicitly for their contribution to heavy equipment mobility, with reinforced bridges, expanded axle load tolerances, and widened corridors reflecting lessons learned from decades of mobility exercises. Sea lift planning incorporated lessons from surge rehearsals, refining convoy assembly protocols and turnaround cycles to ensure that maritime reinforcement commitments matched realistic throughput capacity. Airlift remained a vital component for rapid personnel deployment and high-value cargo movement, but strategic doctrine preserved the primacy of sea and rail for bulk sustainment, reinforcing balanced multimodal logistics architecture. Fuel pipeline networks were expanded and interconnected to reduce single-point vulnerability, while dispersed storage and automated monitoring systems improved both resilience and inventory accuracy. Ammunition management. Systems incorporated rotation schedules and replenishment triggers designed to maintain depth without stagnation, reflecting refined sustainment discipline. Maintenance logistics leveraged modular repair concepts and forward support units capable of sustaining high-tempo operations while minimizing evacuation delays. Intelligence agencies continued to monitor adversary freight movement, industrial production shifts, and infrastructure expansion as indicators of mobilization potential, recognizing that logistics patterns often revealed readiness posture more reliably than public declarations. Satellite observation and signals intelligence supported continuous assessment of rail yard density, port traffic, and depot activity, feeding analytic models that estimated sustainment endurance under varied scenarios. Alliances maintained interoperability exercises focused on customs clearance, rail gauge transitions, and fuel compatibility, acknowledging that bureaucratic friction could impede reinforcement as effectively as physical bottlenecks. Computer-based simulation tools became standard instruments in war planning, stress-testing logistics pipelines against attrition projections and identifying thresholds beyond which offensive momentum would degrade. Contingency doctrine assumed that adversaries would attempt to disrupt supply corridors through targeted strikes or sabotage, reinforcing investment in rapid engineering capabilities and alternate routing pathways. Economic infrastructure development remained aligned with defense objectives, with highway expansion, rail electrification, and port modernization serving dual civilian and strategic roles. By the closing phase of the Cold War, logistics networks were no longer secondary considerations, but measurable components of strategic balance, influencing alliance reassurance, deterrence credibility, and operational feasibility. The accumulated experience of decades of exercises and modeling had demonstrated that the speed of reinforcement, the depth of stockpiles, and the resilience of transport corridors determined how long any conflict could be sustained. Even as political transformation accelerated, the infrastructure built to support potential war remained intact, a testament to how profoundly logistics had shaped military planning. Behind every strategic map and contingency scenario lay an intricate web of rail lines, shipping routes, fuel pipelines, maintenance depots, and storage complexes that quietly defined the limits of ambition and the boundaries of power throughout the Cold War era. In the final assessment of how military logistics networks quietly shaped Cold War war planning, it becomes evident that the credibility of every operational concept depended less on the size of forces assembled and more on the architecture of movement and sustainment constructed behind them. From the early post-war years through the final phase of confrontation, planners in both blocks embedded rail, corridors, sea-lift fleets, airlift wings, fuel pipelines, ammunition depots, maintenance hubs, and industrial conversion capacity into the core of strategic doctrine, recognizing that combat power was inseparable from the systems that replenished it. Logistics modeling matured into a disciplined analytic field, incorporating tonnage projections, consumption rates, throughput ceilings, and attrition curves to test whether proposed offensives could endure beyond initial engagement. Alliances institutionalized interoperability at the supply level, standardizing calibers, fuel types, and spare parts to ensure multinational cohesion under stress. Infrastructure modernization projects were evaluated through dual-use logic, strengthening both civilian commerce and military mobility. Intelligence services continuously monitored adversary freight movement, depot construction, pipeline expansion, and industrial output to assess mobilization potential and sustainment depth. Mobility exercises and war games repeatedly confirmed that ambitious maneuver collapsed when supply projections faltered, reinforcing strategic restraint rooted in logistical realism. Redundancy, dispersal, and rapid repair capabilities were embedded deliberately to mitigate vulnerability, reflecting anticipation that supply corridors would be targeted early in conflict. By the close of the Cold War, logistics capacity had become an implicit metric of strategic balance, shaping deterrence credibility and alliance reassurance even in the absence of active combat. The rail lines, ports, pipelines, storage facilities, and maintenance systems constructed and refined over decades represented a silent architecture of power that defined what was operationally feasible. The Cold War thus revealed that war planning was constrained not only by political will or weaponry, but by the capacity to move, fuel, arm, and repair forces at scale and over time. Behind every contingency map lay a complex network of supply and transport whose reliability determined endurance, and whose limitations quietly set the boundaries of ambition. Military logistics networks, rarely visible in public discourse, were therefore central determinants of strategy, shaping how conflicts were imagined, rehearsed, and potentially sustained throughout the era of sustained geopolitical rivalry.